Hello everyone, this is Radha presenting my findings for Physics 2211 Lab 3 on black holes and orbits. So this lab investigates gravitational motion using computational modeling. The goal is to analyze the orbit of a star around a black hole and then simulate the motion of a spaceship interacting gravitationally with both the planet and its moon. Using Newton's laws and numerical methods implemented in Python through CloseScript, we can estimate the mass of a black hole from observed motion and predict the motion of objects in a multi-body gravitational system. As for the purpose, the lab had two main goals. One, use observed orbital motion to estimate the mass of black hole, and secondly, simulate a multi-body gravitational system involving a planet, moon, and spaceship. And we did this by applying Newton's second law to predict motion computationally. In part 1 of the lab, the system consisted of a black hole located at the origin and a star orbiting around it. The star's position data was generated by the starter code based on my email address, meaning that each student actually received a unique orbital trajectory. In part 2, the system included 3 interacting objects, a planet fixed at origin, a moon orbiting the planet, and a spaceship starting just above the surface of the moon. So the motion of both the moon and the spaceship was influenced by gravitational forces from the other objects in the system. The main physics principles used in this lab were Newton's second law, the definition of momentum, and Newton's law of universal gravitation. And we'll explore them in more depth as follows. Here you can see the model that I received from computing part 1 of the model. And you can see the average black hole mass at the very end, but let's analyze it deeper. So for part 1, the first step was generating a unique orbital trajectory. Then the mass of the star was set to 2 × 10⁻30 kilograms, which was given in the instructions. And next, the time interval between the data points was changed to 86,400 seconds, which corresponds to 1 Earth day. And then the following steps, as summarized in the bullet points, is described in more detail. Several different initial velocities were tested for the spaceship to produce a trajectory influenced by both the moon and the planet. Some velocities caused the spaceship to escape too quickly, while others caused it to crash onto the moon or the planet. And after experimenting with multiple values, finally we decided on -1000, 1000, 0, because this path showed clear gravitational influence from both the moon and the planet without crashing into either object. Several simplifying assumptions were made in this model. First, only gravitational forces were considered. Other possible forces such as atmospheric drag or radiation pressure were ignored. Second, the planet was treated as fixed in place rather than allowing it to move in response to gravitational forces. Third, the simulation uses discrete time steps rather than continuous motion, which introduces numerical approximation errors. Additionally, rounding errors in floating point calculations can accumulate over time and affect the precision of the simulation. And then we had some concept questions. So the first one was the net force acting on the object, whether it was equal to the rate of change of momentum, and what's the differences between them. So the net force acting represents the total physical force applied to it by all interactions, whereas the rate of change of momentum describes how the object's momentum changes over time. So Newton's second law states these two quantities are equal. In the simulation, the rate of change of momentum was calculated directly from the observed motion of the star, and then this was used to calculate the net force. If we wanted to simulate the motion of the entire system more realistically, we would need to include gravitational interactions between every pair of objects. So this includes interaction between the black hole and the star and the planet and the moon and the spaceship. Some interactions would dominate because of larger masses or shorter distances, such as the interaction between the black hole and the star or the planet and the moon. Other interactions would be weaker, but still contribute to the overall motion. Thank you. This code block is the core physics calculation for part 1. So the loop goes through this first position data one step at a time, and each step it builds the initial and final velocity vectors using the x and y velocity components that were calculated from the position data. Then it computes the momentum and finds the change in velocity and change in momentum between 2 consecutive time steps. Dividing the change in momentum by time interval gives dp by dt, which is Newton's second law, which is equal to the net force on the star. After that, the code breaks the net force into parallel and perpendicular components. The unit vector p hat is equal to hat p. Final gives the direction of the star's momentum. The dot product projects the net force onto that direction, giving the parallel component, and then we subtract it from the total to get the perpendicular component. The decomposition is important because the parallel component changes the speed of the star while the perpendicular component changes the direction of motion. In orbital motion, the perpendicular part is especially important because it bends the path of the star around the black hole. So in the next part, we use the force calculated in the previous step to estimate the mass of the black hole. So first we have the r vector, which creates the position vector of the star at the current data point using the x and y coordinates from the trajectory. Then we have r is equal to magnitude of r vector, which computes the star's distance from the origin where the black hole is located. Then the code rearranges the gravitational force equation, and we solve for the black hole mass. Each mass is appended to the MBH list, which you can see, because each loop gives a slightly different estimate at each step. So then we print them all for checking the values and whether they stay in a consistent range. Over here, the code block controls the visualization of the force vectors in the simulation window. So if the magnitude is unequal to 0, that checks to prevent errors, and then it helps to connect the numerical calculations to the physical interpretation. Okay, finally, this computes the average black hole mass from all individual mass estimates collected during the loop. Because the simulation had different masses at different time steps, the values weren't perfectly identical, and so we divide all the values in the list by the number of entries, and which gives us the average mass. Here's the part 2 of the model, where this was the simulation that I got from CloseScript. As you can see, they do not collide, which was actually one of the requirements, but we'll get into more depth now. In part 2, the system became more complex because multiple gravitational forces acted simultaneously. The moon experiences gravitational forces from both the planet and the spaceship. Similarly, the spaceship experiences forces from both the planet and the moon. At each time step, the forces were calculated using gravitational force equation. The net force acting on each object was then used in Newton's second law to update its velocity and position, and it was repeated continuously to simulate motion over time.